Okay. So let's talk about number 10, because if 10A starts wrong, everything is going to be wrong on number 10.
Let's go.
So you got to go OG in the terminology on number 10. So here's this inclined plane. Now, conveniently, it's frictionless, okay? So as soon as you let go of it, what's the only force making it accelerate?
Force parallel.
Force parallel, right? And how do you calculate force parallel?
FG sine theta.
Fg sine theta, okay? So that's the only force. There's no friction, nothing else like that. So because there's no friction or anything else, that force parallel is also your
Force
net
normal.
force. And your net force equals
MA.
MA. Okay? Now, so you got to find the mass of the blocks, which hopefully isn't going to cause you too much pain. Then once you get that net force, then you're going to divide it by the mass and get your acceleration. Then once you get your acceleration, which is a multi-step process, then you're going to plug that into that equation. So you know the length of the ramp, you know how far it goes. So your answer to 10A should be around 3.1 meters per second. Okay? Because if 3A is wrong, everything else is going to be a train wreck. Okay?
It's like baby wipes.
So that should be around 3.1 meters per second. So now that you have that, now we can look at it from a momentum standpoint. So you got another block down here. They're going to hit, and they're going to do the California thing of moving off together. Okay? So here's what you want to do. Because they're going to move off together, the momentum of 1 plus the momentum of 2 equals new momentum of 1 plus the new momentum of 2. But what's the original momentum of block 2?
0.
0, because it's at rest. Has mass, has inertia, it just doesn't have momentum. Okay? So, because they're going to move off together, what can you do here?
Seconds equal.
Factor out that new velocity, right?
What do you mean?
Which is going to be m1 v1. So what you're searching for is that new velocity, which should be 1 and some change. Okay? Now, how do you know that velocity is going to be less than your answer to A?
Because that's to carry more mass.
Has to carry less mass.
What?
Just don't use the word carry. You're right, but just don't.
Move.
Like it has to have the same amount of force on
No.
more mass.
Rhymes with omentum.
Momentum. On
You have to
more-
have the same momentum before and
after.
after. So to create the same momentum with more mass, you have
Less
to be
velocity.
moving
Less velocity.
Slower.
less. You have to be moving slowly. Okay, so that's why you know that has to be smaller than 3.1. Okay? Now, could that new velocity after the collision be a negative value in this case?
No, not in this case.
Why? Because what would that look like?
Like it hits it and then both of them go backwards.
Yeah, you have a block sitting here, a block hits it, and then they start to move up the ramp, which would be cool. Okay? Not going to happen, but it would be cool. Now, when you get to C, there's a couple of ways you could go with C. You could go OG, since that seems to be the theme, or old school. And you could go F equals MA. Now, when I type this up, why did I make that force a negative value?
Because the acceleration was negative.
Yeah, you have a positive velocity and you're slowing down. Okay? That's why I purposely went through and said, okay, that has to be a negative value. So you could go old school and find the acceleration, and then you could go A equals V minus V naught over time. Okay? That's one option. Okay? Now, but make sure that original velocity is the one that you use for your answer to B, because that's how fast they're going after the collision. Okay? Don't use the original velocity of A. Okay? Use the one after they move off. So that's an option. You go old school, F equals ma, find the acceleration, v minus v naught over time. There you go, solve for time. That's an option. If you're going, oh, but Burkamp, I like impulse theory. Fine. You can go force times time equals mass times v minus v naught. You know the force, you know the mass, you know the initial velocity, you know the final velocity, solve for time. You do the exact same math, you just change the sequence, okay? And then there's a couple of different ways you can do D. But on number 10, all of your answers on B, C, and D, and this is an ish, okay? This is an ish. All of your answers on B, C, and D should be around 1. Okay?
3.
You got 3?
It's close to
How big is that ish?
Like
The
point.
biggest variance would be about 0.6. Okay? That would be the biggest variance.
So 1.6.
Okay, now let's talk about number 11 with Huey, Dewey,
But it's not.
and Louie.
But it's not.
Yeah.
Anybody know what Huey, Dewey, and Louie are?
Who we doing? Yeah.
It's from a cartoon.
They're a cartoon.
I don't know which one.
Uncle Scrooge's nephews.
Oh.
Okay. So visualize this. What's the initial momentum of the entire system?
Look at this guy.
Zero,
This
right?
guy.
So at any point afterwards, what does all the momentum have to add up to?
0.
0. Keep that in mind for the lab today as well. Okay? So Huey and Dewey push off of each other. Okay? So when they push off of each other, what has to happen?
It goes slowly.
Yeah, they have to go in opposite directions. Why?
So the momentum still adds up to 0.
So momentum still adds up to equal to 0. Okay, I'm not saying the momentum equals 0. Okay, listen to me very carefully. There's a big difference between saying the momentum equals 0 versus the sum of the momentum still equals 0. Okay, huge difference between the two of them. So basically, one's going in one direction, the other one's going in the
Opposite.
opposite direction. So this is going to have some amount of momentum going this way. Now this one, Dewey, runs into, I don't remember the exact sequence, but they're going to run into each other. Okay? So after that collision, what does all the entire momentum still have to add up to?
0.
0. So just keep that in mind. Just keep 0 in mind when you answer number 11. Talk to me.
Just kind of like a theory question. So since all the momentum has to eventually like equal what it started, right?
Which would be 0 in this case.
Which would be 0, right?
Yeah.
That's for everything, right?
The entire universe.
Yeah, kind of.
What do you mean?
So if
You're gonna ask about the Big Bang.
if I like if I like throw this calculator and it stops, where does that momentum get transferred to?
The Earth.
Okay, so and it just
So,
like absorbs
so
it
every
or what?
time, okay, so this is one of the questions, right?
That's a good question.
So if I give this a push, okay, does the momentum of that system change?
Yes.
Yeah.
And it changes when I push it, okay, and it changes when
It stops.
it stops, okay? So what's happening is that in both situations, and you look at this and go, Burkamp, you don't move, right? Now, let's say I'm in deep, deep, deep space, and I give that a push. What would happen? I'm in deep space.
You'll go
I would go
back.
backwards. Now, I don't do that right now. I don't go backwards.
Right.
Okay, you go, well, the law of conservation of momentum doesn't work. Okay? But here's the deal. I'm not moving when I do this because there's enough friction between the chair and the earth. Okay? So now
Dude, what are you?
what is that noise?
So from the
What are you?
biology.
What are you flexing on me?
So,
Be toward this.
What?
okay, so when I give this a push and I don't move, you sit there and go, well, that's a violation of the law of conservation of momentum because momentum is conserved. But because there's so much friction between the chair and the earth, the earth and I are now part of the system. So when I do this, I have very small, very, 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 very tiny amount altered the momentum of the earth. Okay? This is a law. This isn't just when it's convenient, kind of when it makes sense. Okay? It is a law, which means that that is invariant. The problem is you have to look at like big ideas. And so the same thing happens like when they launch spaceships. Like if you want to go, say, out to like Neptune or Pluto or something. A lot of times what they'll do is here's the sun, here's the earth, and here's, say, Saturn. And you want to get to Saturn. So what you'll do is you'll launch from Earth and you'll slingshot it by Jupiter. And what you do is it's called a gravitational assist. So basically you're going to slingshot it by Jupiter. So what's going to happen is that spaceship is going to steal a tiny amount of momentum from Jupiter. Okay? So now Jupiter becomes part of that system. So we're going to steal a tiny, 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 tiny fraction of that. But it isn't like, oh, great, Jupiter's now going to stop in its orbit because we shot a spaceship by it. Okay? But it is going to take some of that momentum from Jupiter and give that to that spaceship. Okay? It's called a gravity assist. All right. Make sure when you get to that, there's a question like on number 4 with the bullet that embeds itself versus the one that bounces. Keep in mind that demo that we did yesterday. When something hits and bounces back, that's a greater change in velocity and a greater change in momentum than if it just embeds itself and stops. If you don't believe me, ask Louis, because if Louis just catches a tennis ball,
Catches the
that
egg.
takes a certain amount of force, okay? But if Louis hits the tennis ball in the opposite direction, that's going to take a lot more force.
So he hits the egg.
Yeah, when the egg hits the floor, there's a change in the momentum of the egg.
Where's the carton, Louis?
I'll accept
where's
it.
the
I'll
A1
accept it. I'll
carton?
accept the slander until I get the eggs.
Yeah, and until then, okay.
Okay. Deal.
Anyway,
Ooh.
any other questions on the assignment? Devin,
Question number 23. It's
in the book?
Yeah, in the book.
Launched.
I also had
There's
that.
two 23s.
On page 277.
Which
Yeah.
one are you talking about, the question or the problem?
Question.
What you mean?
Question, not problem.
Yeah, not
The
problem.
multiple choice. And by the way, if it's some of you are doing this and it's annoying. If it's a multiple choice answer, what do you think I want written down?
Explanation.
The letter.
I have that too.
Vito is the
Okay?
reason.
Just don't write down the numeric value. I don't have that. I have the letter written down. Oh, that happened the other day and I was extremely frustrated. Anyway, so what page is that on?
277.
I was close. Okay. So here's the deal.
Wiggle.
Is that with the 2 blocks?
Yeah.
Okay. So here's the deal. When you look at this, set this up as saying, all right, 2 blocks, mass 1, mass 2, approach each other along the horizontal frictionless track. Okay. Now, here's the deal. Because they're moving in opposite directions, what do you have to do with one of the velocities?
Negative.
Make it negative. Now, this book always defines anything to the left as being a negative value. So what you can do is you can calculate that initial going M1 V1 plus M2 V2, right? Now, then the 2 blocks then collide and stick together. So this is a California problem. So what's going to happen on the right side of that equation?
It's going to be MA plus MB.
Yeah.
B prime.
M1 plus M2 times B prime, right? So the first thing that you've got to do is you've got to calculate that new velocity. And that should be a negative value. Okay, or at least how I set it up. Okay? Now, then you can calculate the change in the momentum. okay? Because you know, change in momentum is mass times delta V.
Yep.
Now, look at all of those graphs, right? All those graphs can basically be modeled as a triangle. And the area of a triangle is 1/2 base times height. So even though this is a multiple choice question, there's a lot that goes into this choice, okay? So that new velocity, the way I define the system, that new velocity after the collision, I got to be like around -1 meter per second. So then knowing that, then you can calculate the change in momentum, and then you can set that equal to 1/2 base times height. Because remember, change in momentum is going to equal the area, okay? And so if you notice on all of those, the bases, the times, are all the same, okay? So what you're trying to find is that height, which is going to represent that force, okay? So if you do that, it's a little sketchy just because of the way they have it played out, but obviously they're all going to be around,
I see.
start with a 3, but pay attention to the units on that time. That time is in milliseconds.
Do we use 0.8? Is it 0.8 on the? Don't know. I know my book
For what?
for the time. 0.8 or is it 8 milliseconds or?
No, it's like from 15 to 35.
Oh, 15. Okay.
If you look at all those scales, it's all from basically 15 to 35.
Okay.
So your times is going to be 20 milliseconds. But you got to change those into seconds. Okay. All right. Anything else? Going once?
On 20. Well, what's it around? Like, is it a
Which 20?
page 279?
The problem or the question?
Problem.
The problem?
Yeah.
That mass should be between 30 and 35 kilograms.
Okay.
So let me give you a hint on that problem, okay? The hint on that problem is this. Takes a nap in a canoe, wakes up to find the canoe is drifted out in the lake, nowhere stationary. He walks along the canoe at 0.5 relative to the water, and the canoe moves in the opposite direction at 0.15, okay? So if you think about it, here's this canoe, right? Dog's here, here's Lassie. Lassie's going to walk in one direction. Momentum has to be conserved. So what direction does the boat have to move?
Opposite.
The opposite direction. So you have to define one as being positive and the other one being a negative value. So yeah, so that mass on 20 should be between 30 and 35 kilograms.
Number 10, again, what were those numbers supposed to be around? I forgot.
Oh, on my problems?
Yeah,
So
1.
3,
10A
1, 1,
is 1.
No. 10A is 3 and some change.
BC.
Okay.
And then all the other answers on B, C, and D are, this is a ish, are around 1.
Okay.
Got it?
No, I don't got it, but I'll figure it out.
Okay, I have no doubt.
Okay.
And some of your answers should be negative values on the problems that I typed up. Okay, not very many, but you should have at least one negative answer. So if you look through your answers and you don't have a negative value, something's wrong. Now, let's talk about that question number 2 with the brakes, okay? Let me give you a quick lesson on how brakes on your tires work. So, here's like, imagine that you're looking at the front of your tire, okay, so here's the tread. And then you have a rotor, and then you have something called calipers. Okay, calipers squeeze this rotor, and that makes that stop. So here's the difference between like internal and external forces. So let's say that you're driving along and we have an ice storm, and you hit the brakes in your car. Are you going to stop?
Not very fast.
No. okay? Perfectly sheet of ice. So, but are your tires going to stop?
Yes, spinning.
Your tire's going to stop spinning, so the brakes create an internal force. So they stop the tires. But it's the external force of friction which actually makes the car stop. Okay? So it's just like, imagine that I have a balloon here, right? It's filled with air. Well, there's particles inside of that are bouncing around, and that's what gives the balloon shape. Okay? So those are internal forces. They're not going to make the balloon move. Now, I flip the balloon, I apply an external force to it, then the momentum changes. Okay? All right, anything else? Going once, going twice,
Sold.
sold.
Sold. Sold.
Okay, so here's what's going to happen in this lab. You don't have to cough first, that wasn't part of the procedure.
Oh,
That was just, whew, okay.
Death.
So you're going to have two carts, one without a mass, one that's going to have a 500 gram mass. And these are exactly 500 grams, so you don't have to worry about these. So the first thing that you're going to need to do is find the mass of the carts. So how are you going to find the mass of the cart? Take a Newton scale, which is going to measure in newtons. Funny how that works. And then to get the mass, you're going to divide by 9.8. I don't care which one you call cart 1. I don't care which one you call cart 2. Okay? So, here's what you're going to have happen. So, you're going to take one of them. You're going to compress this spring. Here you go. You have the mass on here. Okay? And what you want to do is adjust these positions so that when you release that plunger, they hit the edges of the track at the same time. Okay? So you have three options. We can start it like this, with the heavier mass closer to this side. We can start it just right in the middle, okay? Because they would travel the same distance, okay? Or we can start them like this, with a heavier mass on this side. Keeping in mind, we want them to hit the edge of the track at the same time. So, Becca, where are we going to start it? Middle, closer to the heavier end, closer to the lighter end.
Heavier end,
Why?
because more mass is slower acceleration.
Okay? You're right, but explain that in terms of momentum.
It's dividing by the bigger mass, so I don't know.
No, you're good.
Okay.
Okay, you're good. Let's talk bigger idea, Becca. What's the initial momentum of the system?
0,
0. So afterwards, what does the momentum have to add up to?
0.
0. So let's say this is going to go in some negative direction. So is the momentum of the more massive cart the same as the momentum of the less massive cart?
No. Yes.
Because what's the initial momentum of the system?
0.
So afterwards, what does the momentum have to add up to?
0.
So the only way that can happen is if the momentums are
Equal.
and
Opposite.
opposite. So they're both going to have the same momentum.
Yeah.
And momentum equals,
Mass times velocity.
so if this has more mass, it has to have,
Smaller velocity.
there you go.
Okay.
Got there. Okay, long convoluted, but we got there.
Yeah.
Okay. Now, so what you're going to do is, and this is just going to take a little bit of trial and error. So you're going to just pick a point and you say, okay, hey, let me start here, boink. Okay? And you're going to adjust that starting position until they both hit the edges. Like that was pretty close right there. So, now here's the decision that you have to make. And this is you have to decide this as a group. what we're going to do is that we're going to assume that after the spring's release, the carts are traveling with a constant velocity. Okay, that's the key assumption that you're making. The carts are moving with a constant velocity after the spring is pushed. Okay? So, knowing that, we need to calculate the velocity of the carts after the spring is released. So if we assume that we have constant velocity, what equation can we use to calculate the velocity?
D equals VT.
D equals
VT.
VT, right? So here's the deal. So that means velocity is going to equal distance divided by
Time.
But since we're talking about velocity, we're going to use displacement, okay? Which means it's a vector quantity. So we're going to have one displacement that's going to be positive, the other one's going to be negative. Now, what's the simplest way, we're going to go old school here. What's the absolute easiest way to calculate displacement based upon a subtraction function?
V equals
1/2.
No, easier than that.
It's the new position minus old position.
Yeah, position final minus
Position initial.
P minus P naught, right?
Yes.
Simplest way to do it. Old school, right? So here's the decision that you have to make as a group, okay? You have to decide, are you going to be measuring your positions off of the back of the carts? Because if you're going to go off the back of the carts, like this one would start at 60, and it would stop at 0. So my initial position is going to be 60, my final position is going to be 0. This one, my initial position is going to be like 92, final position is going to be 122. Okay? And that's cool. So, but if you're going to go from outside edges, then you're going to stop them when they get to here. But if you want to go off the insides, and that's cool too, you say, well, I want to start it at 76 centimeters, okay? If you want to go off the center point, and that's cool, then this one, when it gets to the end, then you have to measure off the front of the card here. So here's what you can't do. You can't mark the front edge of the card here, okay, where they're going to go flying apart, and then mark where the back edge of the card is here. Otherwise, you're going to be off by the length of the cart, okay?
Could you just subtract the?
You
do
could.
that and then subtract the
You
card?
could, but then you just, so I don't care how you do it, okay? It doesn't make any difference to me. Go off the fronts, go off the backs, just get a measurement of a true displacement. Now, you already have a measuring device in here. It's measured in centimeters. What do you think, what units do you think you want to work in?
meters.
Meters, okay? So, you're going to use, because this is a vector quantity, you're going to use position final minus position initial. That means one displacement should be a positive value, one displacement should be a negative value. So if your displacements are both positive or negative, you've done something horribly wrong. Okay? One should be positive, one should be negative. So make sure that you attach this 500 gram mass to one of them. Just don't let it float like I've got. Just take a little bit of masking tape or something. You don't have to tape it on so it withstands like, you know, a rocket blast, but you don't want it sliding around either. Okay? So just put a little bit of tape on it and call it good. Got the idea of what's going to happen in the lab. Okay. So, Vitor, give that a spin.
Give it a spin.
So, before you do the lab itself, okay, so let's talk about pre-lab.
Pre-lab.
Pre-lab. So, as a group, you're only going to hand in one per group. You're going to sketch a velocity time graph for the motion of a cart. One's more massive than the other one. Where they're both at rest, you're going to hit the plunger, they're going to go flying apart. Okay? So, keep in mind that you're going to draw a velocity time graph. What's the initial velocity of the system going to be?
0.
After you hit the plunger, are they going to accelerate?
Yes.
then they're going to be moving at
Constant velocity.
constant velocity. Keep that in mind, okay? Now, on the lab, any place where there are asterisks, that's going to require some calculation. And some of these are going to be horribly simple, okay? It might be just position final minus position initial. It might be displacement divided by time, okay? Now, you're going to see two different values of P, and I tried to spell this out. Here it's going to be position final and position initial. Over here, this is going to be momentum final and momentum initial. Okay? Don't confuse the two of them. The first one's position, the second one is momentum. Now, what you are ultimately after, the ultimate goal of this, is that you're going to try and find the forces exerted on the carts. That's your ultimate end goal. Okay? So when you get to that last column, and I see a bracket and it says question number 2. So when you get down here to question number 2, you're going to use force times time equals change in momentum, and the time is going to be 0.0200 seconds, because that's how long it takes for that plunger to expand and push off of each other. Okay? Do not use the entire time that the cart is rolling. We're assuming that the only time that this thing is accelerating or that momentum is changing is when that plunger expands. Afterwards, we're assuming that it's going to move at a constant velocity, and that's what allows us to take displacement and divide it by time. So when you do that last column, I've got that, see question number 2. You're going to use force times time equals change in momentum. At this point, you're going to know the time. You're going to know the change in the momentum. That's what's going to allow you to calculate that force. Okay. Now, when you get to question number 8 on the back side, yes, it was the back side. Okay? So imagine this. We're going to take that cart, or the ramp, but we're going to put a small piece of wood under one end. Okay? Nothing massive. This isn't like we're going straight up climbing Everest or something. Okay? It's just a little block of wood. And I tell you exactly how I want this to play out. The small block of wood is placed under the end of the ramp toward which the more massive cart is going to roll. So here's my block of wood. Here's my 2 carts. This is the one that's going to have more mass. Okay? So imagine that you have it sitting there. You hit the plunger. This is going to go up. And this one's just going to go in that direction. Okay? Now, I tell you, assume that the more massive cart has a positive velocity. Label the point where the more massive cart changes direction. So you're not going to know numbers. You're just going to come up with a general shape. Okay? Keep that in mind. When you answer question number 3, do not even think about answering number 3 on this page. You do not have near enough room. Okay? So answer number 3 on another sheet of paper. Answers on the left, work on the right. Okay? I am done.
Wow.
Man.
You're just gonna let that slide?
It's okay, Mr. Burkham. We enjoyed your speech.
I was excited to do the
Don't listen to
lab.
her.
You're just gonna let that
I
slide?
was excited to do the lab.
Okay.